Hey, my name is Wanxiang. I'm a professor in computer science at UC Berkeley and also the founder of Oasis Labs. Thank you for having me here. Today, I will talk about self-sovereign identity and data sovereignty, building towards a responsible data economy. As we all know, data is a key driver for modern economy and the lifeblood of AI machine learning. More and more data is being collected every day, and value from personalized data is now significant percentage of the GDP, and also global data economy is growing exponentially. However, a lot of this data is sensitive, and how sensitive this data is being used has posed unprecedented challenges for both individuals and institutions. For individuals, individuals have lost control over how their data is used. Often times their data has been sold or misused without users' awareness or consent. And often their data is, this happens under the premise that users' data has been anonymized. However, volume of research has shown that data anonymization is insufficient to protect users' data privacy. Here's a case study done by New York Times, which showed that from an anonymized mobile phone location dataset, New York Times was able to track the location of a Secret Service agent with former President Trump and hence locate whereabouts of former President Trump. And institutions continue to suffer from large-scale data breaches. Many of these attacks, in many of these attacks, attackers steal sensitive information of hundreds of millions of users or even billions of users. And most importantly, a lot of valuable data is still being locked up in data silos due to privacy concerns, and hence cannot be effectively utilized. And these issues will only become more and more severe as we move forward in the digital economy. And hence there's an urgent need for a new paradigm that I call a responsible data economy. What do I mean by a responsible data economy? What are the goals and principles of a responsible data economy? First, we need to establish and enforce data rights. These data rights form the foundation of data economy and help prevent misuse and abuse of data. We also need to ensure fair distribution of value created from data, such that users can gain sufficient benefits from their data. And most importantly, we need to enable efficient data use to maximize social welfare and economic efficiency. In order to build a responsible data economy, we need to make a paradigm shift from today's Web 2 world, where it's platform-centric with centralized solutions, to the new paradigm of Web 3, which is decentralized and user-centric. So first, let's look at some of the key control points in the digital world. In the digital world, one needs to access to resources, access to data, and compute on data. And these are controlled by different mechanisms. And the first is identity, and the access control and data use control. In Web 2, all these are being controlled by centralized third parties. Users' identities are managed by service providers, and users' data is maintained in centralized data silos, and users' data is processed usually without the knowledge of the user. And hence, in the Web 2 world, users are not in control of their data at all. In the Web 3 world, we hope to make the shift from the centralized control to decentralized user control. And these are accomplished through decentralized identity, decentralized access control, and the policy-compliant decentralized computation, which enables self-sovereign identity, self-sovereign data access, and self-sovereign compute. And thus, in the Web 3 world, users can control how their data is used without relying on an intermediary. So first, let's look at decentralized identity. So in Web 1.0, users use username and passwords for their identity and authentication. And in Web 2.0, users rely on service providers oftentimes for their identity management. And in Web 3.0, with decentralized identity, users can control their own identity through public key cryptography. Essentially, users own their identity and control their identity by controlling their own private keys. So with decentralized identity, there's more that we can enable using more advanced technologies. In particular here, let me share briefly about a recent project that we have done on anonymous credentials. So with anonymous credentials, users, certificate authorities issue credentials to users in a privacy-preserving way, and users can then use these anonymous credentials to prove certain properties of themselves that has been certified in the anonymous credential. And users can do this, again, in a privacy-preserving way so that they can remain fully anonymous, but at the same time, still be able to prove, for example, they are over age 18 and other attributes and so on. So in our recent work, SNAC, we built the first ZK SNAC-based anonymous credentials to enable efficient on-chain verification. In this case, with users with the issued anonymous credential, they can generate proofs, for example, that they are over age 18, or they are a student at UC Berkeley, and so on. And then these proofs can then be verified on-chain by a smart contract. And in this case, enabling users to be able to utilize certain services based on their attributes. And we utilize advanced cryptography, for example, using proof recursion for proof batching to further optimize the efficiency of on-chain verification of these anonymous credentials. And we also provide full support for revocation, auditability, and certificate authority, anonymity, and so on. And a great use case for this ZK SNAC-based anonymous credential with efficient on-chain verification is to enable KYC DeFi. So in this case, a user can go through a KYC process. A certificate authority checks that user has gone through a KYC process and then issue an anonymous credential for the user, indicating that the user has gone through KYC. And now, using this anonymous credential, users can join on-chain DeFi services and applications and be able to verify that they have already gone through KYC. So this can enable KYC DeFi that both protects users' privacy and also are regulatory compliant. With our new cryptographic schemes, we achieve orders of magnitude performance enhancement over previous non-ZK SNAC solution-based approaches. And with our solution, this is the first time where KYC DeFi can be made practical. So that's an example how self-sovereign identity and anonymous credentials can help users to maintain control of their identity and being able to utilize on-chain services in a privacy-preserving way. So next, let's look at additional capabilities that users can have with self-sovereign data and compute. So first, in order to enable self-sovereign data and compute, we need to develop new solutions. Traditional solutions in Web 2 are insufficient. In traditional Web 2 solutions, data is only encrypted and at rest or in transit, and hence data encryption can only protect data at rest or in transit. And data is either not used or is copied once used, and making it difficult for data owners to control the usage of their data. And I already mentioned that data anonymization is often insufficient to protect users' data privacy. And in summary, in Web 2, users have no control how their data is used. So instead, in Web 3, we need to develop new technologies to enable data protection in use. And this has several different aspects. One needs to be able to control the use of data without copying the raw data to be able to compute on. And two, we need to be able to protect computation outputs from leaking sensitive information and ensure policy compliance for data use. And with these capabilities, users can control and audit the use of their data without relying on central trust. Luckily, there has been rapid advancements in both research and industry in what I call responsible data technologies. A number of different types of technologies, when put together, can help enable responsible data use. So these include secure computing, such as using secure hardware, cryptographic methods, such as secure multi-party computation, fully homomorphic encryption, and so on. These secure computing techniques keeps data confidential during the computation process. And differential privacy helps ensure computation outputs won't leak sensitive information about the input. And federated learning enables distributed data analytics and machine learning when while data does not leave user's device. And with distributed ledger, it helps provide a immutable log of the user's data use policy and how data is being utilized to ensure data usage is compliant. So here I want to give a real-world example of how such a secure computing technologies can help user maintain control of their data while still enabling data to be utilized in a privacy-preserving way. So this is a recent project that's done in partnership between Oasis Labs and Meta, and together with a few other universities participating as well. This is the first of its kind large-scale AI model fairness measurement. So AI models are now prevalent. So for example, at Meta, AI models are used for recommendations and for personalized services for users. And as a society, it's important to know whether these AI models that are used widely, whether they are fair or whether they have biases. And the question is, how can we do these AI model fairness measurements? In particular, in this case, in order to assess the fairness of an AI model, the model provider needs to the computation needs to be based on both inference results from users as well as knowing sensitive attributes of users. So in this case, for example, Meta as a model provider can know the AI model inference results for a given user, for example, a given user ID. But Meta doesn't know the sensitive attributes of the user, for example, user's gender. And separately, users could opt in for a certain survey where they would provide their gender information, for example, to a survey operator. And the AI model fairness can can be measured using different metrics. Here, as for simplicity, one example here is to compute and compare the average inference results of users based on their gender. And hence, by comparing this average inference results of users based on their gender, we can know whether the AI model here is fair according to based on users' gender. So the key question here is that how can we enable this AI model fairness measurement in a privacy-preserving way? In this case, the model provider knows users' inference results, but doesn't know users' sensitive attributes. And the survey operator knows users' sensitive attributes, but the survey operator doesn't know users' model inference results. And hence, we need to be able to compute the final results of the fairness calculation by utilizing the data from these different data sources, and at the same time to ensure privacy protection. So this is what we set out to do, working together with Meta. And the technology that we have developed combines the different privacy computing technologies. So first, by using MPC, secure multi-party computation, the survey operator secretly shares users' sensitive attributes across multiple facilitators. And in this case, 3 universities actually joined as facilitators. And the Meta, the model provider, in this case, generates homomorphically encrypted results for the inference results for the corresponding users. And also, it provides zero-knowledge proof that the encrypted inference results actually is well-formed and falls within a range. And it then sends this homomorphically encrypted results to the facilitators, which use the information together to compute the encrypted results of the fairness calculation. And the facilitators here also adding differential privacy noise to further protect users' data privacy. And in the end, the fairness calculation result then can be achieved in a privacy-preserving way. So this is the first of its kind of a large-scale real-world deployment of a privacy computing technology and being used for a really important task for AI model fairness measurement. And we also have developed a new open source platform to help make such decentralized data science even easier by bridging the gap between cryptographic protocol design and real-world deployment, and to make cryptographic protocol deployment orders of magnitude cheaper and faster. And so this platform called CoLearn is a new open source platform that makes protocols composable in a unified framework and builds a preset of carefully designed, standardized, decentralized programming abstractions. And it takes advantage of the recent deployments in cryptography and privacy-preserving technologies. CoLearn provides a unified platform for decentralized data science that reduces the time and effort from design to deployment for new protocols by orders of magnitude. That can reduce the work that often times takes months to only a few weeks. And also make it much easier for developers to utilize existing cryptographic protocols. And CoLearn today integrates already with a number of state-of-the-art cryptographic protocols for privacy-preserving machine learning and federated learning and so on. When we combine privacy computing and blockchain, we can enable a new type of assets that we call data assets. With blockchain, it helps provide a immutable log of users' data use policies and how the data is being used. And with privacy computing, it ensures that data remains private even during the computation process. And when we encapsulate the data and the data use policy together, it creates an asset that can be consumed along these guidelines and help users to be able to benefit from their data. So with data assetization, the Oasis platform can unlock a new responsible data economy where users and businesses can maintain data rights and earn value from their data assets. And we have applied it as an example for the genomic data use case. And as we all know, user genomic data is one of the most private data source for users, and is incredibly valuable as well. And users often have concerns how their genomic data is used when they utilize genomic data analysis services. And with Oasis, for the first time, we provide a platform to help users to maintain control of their genomic data and how their data is being used, and enable users to benefit from their genomic data while still protecting their data privacy. And when we put these different components together, the community can together form data commons and data DAOs for decentralized data science. So in this case, data owners and data producers, they can register their data sets with policies specified. In particular, they can join certain data DAOs that specifies the policies of how the data in this data DAO will be used and how the rewards will be shared. And the data consumers and data analysts then can search through these data DAOs to find the relevant data and write data analytics and machine learning programs over these different data sets and data sources. And these data analytics and machine learning program can then be run on the distributed secure computing platform while ensuring that the program is compliant with desired policies. With this approach, we can reduce friction of data usage, remove data silos, and enforce stronger security and privacy protections. I strongly believe that in 10 years, data trust and data commons will become predominant ways of utilizing diverse sources of data, enabling ownership economy where users benefit from their data as owners and partners. And in 10 years, huge economic value will be created through these new forms of data trust and data commons, all just a magnitude higher than today's data marketplace. To summarize, by shifting from centralized control in Web 2 to decentralized user control in Web 3, we can help users control data usage without relying on intermediary. And so with this paradigm shift, it can help us build a responsible data economy. And for the future of the internet, we must build a responsible data economy. And the decade of 2020 is the decade for building a responsible data economy. Thank you.